And I think we've gotten through to about this point right here, where we were talking about how the mucosa is formed. And yesterday in lab, we looked at a bunch of slides that allowed us to see this pattern. So when we're dealing with the large intestine, then it's a downward fold of the mucosa that increases surface area. And then what was unique we talked about yesterday in lab was that the other organ that would have a downward fold of the mucosa would be the stomach. But in the stomach we have goblet cells at the neck, and then they convert to parietal cells and chief cells as we go downward. And what's unique in the large intestine is that the goblet cells continue all the way down the intestinal gland to the bottom. So kind of a unique relationship where you can see the droplets of mucus all the way down. Okay. So in the large intestine we have primarily two glands, two cells that make up these intestinal glands. So the goblet cells, which secrete mucus that protect the lining of the large intestine so that we can have an environment where bacteria grow, that the bacteria can't get through the lining into our blood. So we have this mucus lining, and also help us prevent digestion, because all the digestive enzymes that we added in the stomach and in the small intestines are still in this material. And so we have digestive enzymes, so the mucus is really critical. And then the end products of the digestive enzymes and what we've added now is bacteria that help us continue some digestive processes and make some important vitamins like vitamin K and B. At the top, where the downward folds start, we again have microvilli cells, which are absorptive cells. That's a pattern that we saw in the small intestine. And the difference was in the small intestine, the absorptive cells were at the top of villi, so they extended into the lumen quite a bit. Whereas here, the absorptive cells are just in the lining of the mucosa where it's kind of flat before the downward folds. And then they're very critically important for the absorption of water and some other things. So what we absorb through the gut lining, the bacteria and stuff, is also electrolytes. So electrolytes are very important. We're going to deal with electrolytes in the next unit when we deal with the kidney, because the kidney's role is to help maintain electrolytes as well. But electrolytes are critically important for our normal physiology in terms of nerve impulses and some other things. So it's very critically important that we conserve them from food material that we ingest. So after about 3 to 10 hours, about 90% of the water has been removed from the diet. So remember, we went through that pattern of how much water was actually added to this process of digestion. And so in about 10 hours, we recovered most of that water so that we can recycle it, which is very critical to maintaining our health as well. And then what we do is we convert this real liquid chyme to a semi-solid, which we now no longer call chyme but feces. And then feces is going to consist of dead epithelial cells. So you're constantly replacing the uncharacterized stratified squamous from your esophagus coming down. You're constantly replacing the simple columnar cells that line the stomach, the small intestines, and the large intestines. So epithelial cells are highly mitotic, and we constantly replace them to keep that surface healthy all the time. So where the cells end up is either being digested by the digestive enzymes as they're sloughed off, and we recycle the material, or they end up within feces as cellular debris as well. And so one of the things from a clinical standpoint is when you have patients who are dealing with cancer and they're on chemotherapy agents, then chemotherapy, the target for chemotherapy is active mitotic cells. So that's why the hair stops growing and you get hair loss with chemotherapy. But one of the other side effects of chemotherapy is a lot of change in digestive function as well, an increase in diarrhea events, an increase in nausea, a difficulty in actually absorbing food material because the lining of the digestive system is all highly mitotic. When you arrest the mitosis, then the lining begins to suffer while they're on the chemotherapy, and it takes a while after they're off for their digestive system to actually come back to normal of when they can undergo mitosis again. So it's one of the side effects of chemotherapy that we see. And then the other thing we see is a lot of undigested food materials such as cellulose. So we lack the enzyme to digest cellulose. The bacteria in our gut lack the enzyme to digest cellulose. So the plant material we ingest and the cell walls of the plant material we ingest then become fiber in our diet because we lack the enzyme to digest cellulose. The bacteria lack the enzyme to digest cellulose. And then what we know, if we look at cancer events in the digestive system, so GI cancer like colon cancer and stuff, that the amount of fiber in your diet is critically important to maintaining a healthy digestive system. So having that cellulose is present. So what's interesting, if you think about our history on Earth, is that before we harnessed fire to actually cook food, we were eating all raw material. So raw vegetable material, raw animal material. And that's what our digestive system was really designed to do. And then when we learned to use fire, we just pre-softened it to digest it. So it's kind of interesting. So we have a long history of this cellulose being a very important part of our diet. And then because we have bacteria, we're going to have a lot of live bacteria and dead bacteria. So that creates the dilemma with feces and managing it on a broad scale, like a city of Spokane, is that all the feces contains live bacteria. And that live bacteria, if it's not in your gut, but in the upper part of your digestive system, makes you really sick. And so we have to manage it for that. And then, as I said, we have 1,000 species of bacteria in our gut, and there's a population control based upon the species that are most dominant because they modify the environment. So the one that's most common is E. coli. And so E. coli reproduces itself every 12 minutes in your gut. Because we have the perfect environment for that as long as there's a food source. We have the perfect temperature for it. So every 12 minutes, one E. coli becomes 2 E. coli. And then those 2 E. coli become 4 E. coli. And 4 E. coli become 8 E. coli. So you can see that we have this amazing ability to produce bacteria. And so because we couldn't maintain that population, then a lot of bacteria die and a lot of them just are excreted in the feces to try to maintain the population. Yes?
Are the bacteria in your gut managed only by your systems, or will they feed on each other?
They don't actually feed on each other. They do out-compete each other. Okay. So that's how the population is maintained in your gut. Is the dominant bacteria create an environment that enhances their capacity to reproduce. So they become the dominant one, and they limit the bacteria, the other types of bacteria that are there. So if you take antibiotics, heavy antibiotics, what you end up doing is altering the flora in your large intestine. So one of the things that happens is E. coli drops, and then other bacteria then become more numerous. And so that's one of the reasons why there's a reasonably common connection with antibiotics and diarrhea, because we've actually changed the flora in our gut. And then what happens with really potent antibiotics is that if we change the flora too much, there are a couple of species that are really kept in check by the dominant bacteria. And when they become more numerous, they really irritate the gut lining. And so then people will have bloody diarrhea. And it was caused by the antibiotics we took to cure something else. So then you have to go in and get a bunch of other medicine to keep yourself from dying from this shift in gut flora. Yeah. So it's really kind of a cool process.
A lot of people see it.
Pardon?
See it.
Yeah. So one of the ways that, if you're on antibiotics, so one of the ways that you can actually manage the the relative population in your gut is actually to use active culture yogurt. And active culture yogurt is non-pasteurized yogurt, so it's fairly easy to find in health food stores. And if you look on most of them, they're labeled and they actually show you the bacteria that's in there. And there's usually between 6 to 10 species of bacteria that's actually in the culture yogurt itself. And that helps you. It's actually something to do after antibiotics. If you eat yogurt, active culture yogurt, you can re-inoculate with the good guys. All right. So just as a summary, so one of the key roles of our large intestine then is to absorb water and to absorb electrolytes, and then to absorb some vitamins, particularly the vitamins that the bacteria in our gut actually produce. Right? And then the end product of absorption then is going to be feces, which we just said is actually going to develop in the transverse colon. And so it's going to consist of some water, and then that's the key to diarrhea versus constipation, is actually how much water is retained within the feces. And it's going to have a lot of inorganic salts, sloughed out epithelial cells, bacteria, bacterial products, and undigestible food parts. And then, although most of the water is, as we've talked about, kind of review, as most of the water is absorbed by the ileum, and the jejunum, the large intestine is what really has to fine-tune that to help maintain water balance. And we're actually going to look at water balance in more detail in the next unit, because we're going to deal with the urinary system. And its primary role is water balance, along with excrement. Okay. So once we form feces in our transverse colon, then what actually happens is we have a couple of reflexes that we talked about that then kind of control the movement of feces from the transverse colon into the rectum so that you can defecate. And so the whole process is tied to adding new material to the top of the digestive system and then vacating the lower part of the digestive system so that there's room for the new material coming down. So the one we talked about was a gastrocolic reflex, where distension of the stomach causes mass peristalsis to move the material from the transverse colon into the rectum. And then the other one was the ileocecal reflex. So the ileum itself, the lower part of the small intestine. And so what you're trying to do is make sure that as you put material in your stomach, you're going to have room in your small intestine to manage it in a couple of hours. And then once the material is passing out of your stomach into your small intestine, you want to make sure that the large intestine has room for the material that's coming down. So the two reflexes kind of connect to managing the movement through it. And so what happens when you extend the rectum, you end up with what's called a defecation reflex. And so a reflex, if you recall from our talk with the nervous system, requires you to have sensory input, so you have to have receptors. Then a receptor sends signals to the central nervous system. The central nervous system then interprets those receptors signals and then sends a signal back via motor nerves to an effector. So in this instance, the effector is going to be muscle, both skeletal muscle and smooth muscle, that we're going to use to create a defecation. Okay? And so the muscles that we use, because we use two primary mechanisms for the process of defecation. One is just the smooth muscle in the rectum itself, so we can actually shorten the rectum because of the longitudinal muscles that are in the wall of the rectum. And then the other thing we use is a big increase in abdominal pressure. So to increase abdominal pressure, we can use our diaphragm by dropping our diaphragm more, which is going to increase abdominal pressure. And we can use abdominal muscles to compress the side walls of the abdomen to increase that pressure. So we're getting voluntary contractions, which are the ones we control, of the diaphragm and abdominal muscles, and then the external anal sphincter, and then we have the internal anal sphincter that's actually going to be involuntary. So again, that's why infants can't postpone defecation. So once the signal's been sent, the internal anal sphincter just relaxes and they defecate, which is why they have to be in diapers. So it isn't until the brain connection to these muscles, these skeletal muscles, maturates so that they can actually physically control the contraction of those muscles, that you can actually learn to postpone defecation so that you can be potty trained. So as we said, the gastrocolic reflex moves feces from the transverse colon into the rectum, and then stretch receptors within the rectum itself send signals to the sacral part of your spinal cord, and then it becomes a parasympathetic reflex, and parasympathetic nerves are going to control the muscles of the rectum and relax the internal anal sphincter. So that's the part that is involuntary, is the parasympathetic branch of the nervous system. That's occurring in babies. And so the part that we learn to control in is our external sphincter with voluntary control. And because this is a parasympathetic reflex and it's modulated by the sacral plexus, then oftentimes if we have people that are quadriplegics or paraplegics that have had lower spinal cord injury, they actually have trouble with the defecation reflex because it doesn't work as well as it does with trauma to the spinal cord itself. All right, so the two big concerns from a clinical standpoint with defecation goes back to water and the ability to absorb enough water. So if you have diarrhea, it's because the chyme is actually being moved too quickly through the intestine, so through the jejunum and ileum and the large intestine. And so because the transit time is really quick, the absorption is limited, so you end up with really, really watery stools. And the problem with that over the long term, if it's really bad, is it dehydrates you and you lose electrolytes. So you have to either use Pedialyte or something that we've talked about, or you have to have IVs because you can die from it. So things like cholera kill people simply because they have such bad diarrhea and they're so nauseous they can't hold anything in their stomach and they really become compromised with electrolytes and water. So the inverse is constipation, where we have a decrease in the movement through the GI tract. And so there's too much water is being reabsorbed, and the stool has become really hard. So from a clinical standpoint, that's always something of concern when somebody's been in the hospital for trauma and/or had surgery, because when you're under an anesthetic during the surgery, the smooth muscle contractions of the gut are really, really slowed down. So it makes you nauseous in your stomach, which is why you can't eat before a surgery, because you become nauseous with the anesthetic. And then what actually happens is in the small and large intestine, the peristaltic movements are limited. So we begin to slow down this process, and we absorb way too much water, so the feces becomes more semi-solid and high. And then what can happen is that can cause an impaction, where the feces will no longer move. And then one of the classic ways you would discover that is that the person would eat and then vomit, because they're putting stuff in their stomach, but it can't go anywhere. So once it's there, then the only way the body gets rid of it is through vomiting. So that's always a concern post-operatively. That's why they listen to bowel sounds by using the stethoscope over here on your left side where the descending colon is, because they can actually hear the sounds made by postural churning as it moves down through the large intestine. And they also don't release people until they've had bowel movement, because they don't want to send you home with a bowel impaction. And then the other area where it's always a concern is in elder care, particularly when people are becoming less mobile and they're more confined to wheelchairs and lower beds, then bowel impactions become more problematic as well. So it's always something to check to watch.
How far would the body have to get backed up before it will refuse to allow you to take in more food?
Well, you'll just eat and vomit.
Yeah, but are there signals sent in the colon that say, "Hi, we're backed up. You can't eat anymore," or would it have to back all the way up to the
Yeah,
side?
I'm sure there are. My only experience was with my parents who have dementia, so there's an added problem in that the brain is not working well at all. So my stepfather had an L3 and 4 compression fracture from osteoporosis in his lumbar vertebrae. And he went from being able to walk around and move to not being able to get out of the bed for several weeks. And he got a bowel infection during that period of time. But he would want to eat, and he would just vomit. So the people at the Holy Family didn't really like him too much. Because he would just vomit all over the floor. Because he had dementia. And they would leave you notes saying, "Push the button if you feel nauseous." And I was like, "Yeah, right. He's going to remember to do that." So one of the concerns we have with our colon, particularly with the movement of material through it, is that we know that if material is retained for a while, it irritates the lining. And as the lining becomes irritated, then we increase mitosis to compensate for that irritation of the lining. So one of the things we're always concerned about as you age is that the lining, as it replaces itself, will develop little polyps, and then these polyps can actually convert to cancer. And so the coloscope is how we do it, which is a long flex tube. And I showed you the pictures yesterday in the lab where you can actually go in the anus and go all the way into the ileum and go around all of the small intestine. And they actually take pictures, and they have a video as they're doing it, so they can look at the lining to see that it's okay. The other way that you could do it is through screening for blood in feces itself. So if you have blood that's entering the feces really low, like in the rectum or anus, it's going to look like blood. It's actually going to be red and look like blood. But if the blood is actually entering the digestive system higher, then it's actually you're actually going to begin to break down the red blood cells, and then you're going to free up the hemoglobin. And then when the hemoglobin gets tied into feces, the iron in the hemoglobin makes the feces black. And so black feces is usually indicative of the presence of blood in feces. But it takes quite a bit of iron to do that. So if you take iron supplements, oftentimes one of the consequences of iron supplements is constipation of the black feces, because you aren't absorbing it as well. Which is why when people become really anemic, they now do iron infusions through IVs, because it's easier to get blood through that line. All right. So the two organs that we haven't talked about that are critical to the digestive components in the small intestine are two organs that are actually associated with the duodenum. So in this model, the stomach would be over here, and this is the duodenum. So the duodenum makes a big curve after it's connected to the stomach. And what sits in the curve is this gland right here, which is the pancreas. Okay. And then the pancreas is actually going to have connections to the small intestine so that it can put products directly into the duodenum itself. And then the other gland we're going to talk about, which is in the upper right quadrant of the abdomen, is the liver. And then the liver also has a duct that comes down and empties products into the duodenum itself. So all the organs we've been talking about, with the exception of the salivary glands that we already did, are the organs that comprise the main portion of the GI tract. And so the liver and the pancreas are considered accessory organs because they have products into it that are going to help with digestion. So what we're going to do is we're going to look at the pancreas first, and then we're going to look at the liver. And then that's what we're going to do Monday in lab, is to go over this with models and with slides again. So this is a fresh cadaver, just not preserved like the ones in the lab, so that's why it's nice and pink and shiny. So this is the stomach, and look at these great folds here, which are rugae, that are in the stomach itself. And so then this is the body of the stomach we're seeing right here. Here's the antrum of the pylorus. Then we see the pyloric canal tapering to the pylorus, which is the sphincter that controls the emptying of the stomach and the opening through it. So then here's actually the duodenum. So what they've done is they've actually, the pancreas set right here. And this is actually the shape of the pancreas. And what they've done is they just flip the pancreas over so you can kind of see that relationship. So this is the pancreas right here. So the pancreas has a large portion that we call the head. And the head sits in this curvature of the duodenum. And then it has a tapering portion that we call the body. And then when it becomes to form to a fine point toward the end right here, we call it the tail. So we have the head of the pancreas, we're seeing right here, the body of the pancreas, we're seeing right here, and the tail of the pancreas, we're seeing right here. And so what happens is the pancreas is an aggregate of cells, and all the cells are associated with small ducts. And then all the small ducts come together to form larger ducts and larger ducts. So at the point we talk about the pancreas, then the only thing we're going to talk about are the two largest ducts that are formed by all these small ducts coming together. And so what we have is we have two ducts that actually drain the pancreas and into the duodenum. So the largest one is called the pancreatic duct, or the duct of Weyerson. And then a smaller one is called the accessory duct, or the duct of Santorini. And so what we're going to do is we're going to look at a picture in a second that kind of shows you how those run through the pancreas and how they dump into the duodenum. Okay. So much of the pancreas is made up of cells that produce bicarbonate and digestive enzymes and help us digest food material that's been previously processed by the stomach. Right? The other part of the pancreas, which is only less than probably 5% of the pancreas, are islands of cells that look different than all of the other cells in the pancreas. So they're called pancreatic islets or islets of Langerhans. And islets of Langerhans actually produce hormones. So the pancreas actually fits into two body systems. Fits into the digestive system because the production of digestive enzymes and pancreatic juice. And then it also fits into the endocrine system because these islets of Langerhans produce hormones. So that's kind of what we're going to talk about is the two parts of the pancreas and the role that they play. And then in the lab on Tuesday, we're actually going to look at the pancreas under the microscope and we'll be able to see these cells in detail. So the pancreas itself produces about 1 liter to 1.5 liters of pancreatic juice. And the main component in pancreatic juice that is very important to the environment in the duodenum is the bicarbonate. And so the bicarbonate is a buffer. So remember, the chyme coming out of the stomach is a pH of 2, and it's very, very acidic. And that allows us to soften all food material. So I'm going to show you an example. It would happen faster in the stomach. But so I always tell the students in 241 that if you soak bone in acid, it takes all the mineral salts out of the bone. That's how dogs eat bone. So this is a turkey bone that was soaked in acid and is now like rubber because all the mineral salts have been eaten out of it. So that would be our first step in being able to digest bone, would be demineralize the bone. And then we would have enzymes then that would help us digest the collagen, which would be the other major component of the bone matrix. And that's what's left is the collagen. Isn't that crazy? Yeah. Actually, Dan did this. because he took my class and he didn't believe me. No. So he's telling lies. But it's vinegar.
I was just, okay, because I went to the preschool and we used to soak eggs in
Yeah.
the shell would disappear.
Yeah, you can dissolve the shell around an egg, and the vinegar also interacts with the egg white. It looks like the egg's been hard boiled after it's been in acid for a while. I don't know if either of yours did that or not.
No, I was just saying that we went with water.
Yeah.
You probably wouldn't have.
Yeah, or it didn't have strong enough acid. So vinegar has acetic acid in it, but it's a real dilute acetic acid. So in a lab, if we wanted to do this, we could use a little stronger acetic acid, and it would do it much quicker. And one of the reasons why dogs and cats can eat bone at a greater rate than we do, they can eat things that would make us really sick, is their hydrofluoric acid in their stomach is even stronger than ours. That's how dogs can eat cat poop for a diet. Or we can't. All right. So just to summarize, so we have acid in our stomach so we can dissolve food. But the dilemma with the acid in our stomach is most of the enzymes that we use to digest food will not work in an acidic environment. So what we have to do is as the chyme is exiting the stomach, we have to adjust the pH to a basic pH, so above pH 7, so that the enzymes that we need to continue the digestive process can actually work. So if you think about it, one of the enzymes we talked about in the mouse, salivary amylase, begins the digestions of carbohydrates, complex carbohydrates. But as soon as that material enters the stomach and becomes really acidic, salivary amylase stops working. Okay, and you don't do any carbohydrate digestion. So when it enters the small intestine again, then we're going to shift the pH, and it actually is going to change the shape of the protein molecules in the enzyme. And if the enzyme wasn't broken down by pepsin, which was the proteolytic enzyme added to the stomach, then the amylase would become active again with a shift in pH. But what we also do is add more amylase from our pancreas so that we can continue the process of carbohydrate digestion in that basic pH. So what we were talking about is here's the head, here's the body, here's the tail, and it fits in that nice little loop of the small intestine. And so we have this one main duct that runs from the tail all the way through the body. And that's the pancreatic duct, or the duct of Weyerson. And then what it does is it drops inferior in the head of the pancreas and goes to the small intestine. And we have a Y off of it that goes to the small intestine up high. So this upper one is the accessory duct, or the duct of Santorini. And then this long one that drops down is the pancreatic duct, or the duct of Weyerson. And so that allows us to actually add bicarbonate and digestive enzymes at two places in the duodenum. So we can add it from where this duct opens up with the duct of Santorini, or we can add it with where the pancreatic duct comes in. And then that is where the duct from the liver, which is, you can barely see here, which is common bile duct, and the duct of Weyerson come together, and they form that hepatopancreatic ampulla that we talked about, and we'll look at in the lab on Tuesday. It's also called the ampulla beta. So over here, you can actually see the duct of Weyerson. You can see the common bile duct come together. They create this kind of vase-shaped structure that we can actually see, which is the hepatopancreatic ampulla. So hepato, liver, pancreatic, so it's telling you that what two are coming together. And then that projects through the wall of the duodenum. And where it does, there's a little finger-like projection into the lumen of the duodenum. And so that's called our duodenal papillae. And so they call it the major duodenal papillae here, because we have a smaller one here, where the duct of Santorini comes in. So we actually have a major and minor duodenal papillae.
Does the duct from the liver also join with the accessory duct?
No.
No. So
Just
the pancreas.
the duct of Weyerson in most people.
Yeah. So-
like we always say, there's always genetic variations, and so you get these little weird things that happen. Yeah, but that would be common. And then because we want to, if there's nothing in our duodenum, then we don't want to release these products. Then we actually have a little sphincter where it passes through the wall of the small intestine. So that's called the sphincter of Oddi, or the sphincter of the hepatic, pancreatic, and so those are kind of the anatomy of it. And so what we're going to do is we're going to produce about 1.5 liters of pancreatic juice that's rich in bicarbonate, but it is also going to contain some salts and some digestive enzymes. And then the salts are going to make sense when we look at absorption, on how we absorb things. Okay? So when we look at the pancreas, we can divide the pancreas into 2 populations of cells. And the most common cells are these cells out here, which belong to these aggregates called acini. And so the cells are called acinar cells. And so it's all of this part of the pancreas that dominates the pancreas that actually makes the bicarbonate and the digestive enzymes. So the acinar cells are responsible for producing bicarbonate and digestive enzymes. This population of cells here that's structurally very different from the rest of the pancreas is an islet of Langerhans. And that's the hormonal component of the pancreas itself, right? And when we look at an islet of Langerhans, I didn't order one in because the cost just gets pretty expensive when you have multiple stains done on a single slide. But if you stain specifically for certain compounds, you could actually stain the different cells in an islet of Langerhans, so you can see different cells. So our stains are more generic stains, so they're just all going to look like a similar cell mass. But what there are 4 distinct types of cells mixed in this. Okay? And so alpha and beta cells would be the most common cells kind of at the boundary of the islets of Langerhans. And these 2 are hormones that are antagonistic to one another, meaning having opposite effects. And so alpha and beta cells help us control blood sugar. So if you have juvenile onset diabetes or type 1 diabetes, for some reason all of your beta cells disappear. And we think it's an autoimmune response or attack on the beta cells. So since all your beta cells are gone, you don't produce insulin. And insulin is required in your blood to bind with sugar so that your cells recognize sugar. And so one of the early signs of diabetes would be children that have to urinate frequently, and in their urine has a lot of sugar in it. And in normal physiology, there's just not a lot of sugar dropped in urine because that's our #1 favorite thing to use to make ATP. And so we just don't do it. So that would be one of the signs. So the other thing we see in the aging population, particularly an aging population where we're a little overweight and consume too many alcoholic beverages, is that the beta cells' response to blood sugar drops. And then we end up with what we call type 2 diabetes, which is where the beta cells are still there, but the response to elevated blood sugars doesn't cause an increase in insulin like it did originally. So then you can manage that diabetes with diet, exercise, and weight loss, whereas type 1 diabetics actually have to inject insulin. And if you were a type 1 diabetic in the 1800s, when you were diagnosed, you probably had less than 10 years to live, and you were going to die from it in 10 years. So there's a really cool story about how we discovered insulin and how we learned to use it in terms of as a remedy to diabetes. So what actually happens without insulin is you don't recognize sugar, you don't absorb it through the gut lining well, you pee it all out, so your body begins to use proteins for ATP, and you begin to self-digest all of your muscle mass and your organs. So it's a wasting syndrome where you just simply starve to death over time, even though you're ingesting, because you can't make ATP in a normal way. And so they would just waste away and eventually die from that. So the way it works is alpha cells produce glucagon. That is a hormone that elevates blood sugar. Beta cells produce insulin, and that is a hormone that decreases blood sugar. So if you eat a meal rich in sugars, then what the normal physiology would be is as the sugars enter the small intestine, begin to be absorbed by the blood, then beta cells would increase their production of insulin. The insulin would bind with sugars, and that would cause you to take the sugars up, use them to make ATP, take the sugars up, use them as a storage product, being glycogen, or take the sugars up and convert it to fat if you have all the others in abundance. And then if you fasted for a while and your blood sugar dropped, then what would happen is alpha cells would release glucagon. And that would cause the liver and skeletal muscle to release the stores of sugar in forms of glycogen back into the blood to elevate your blood sugars. So these two hormones are antagonistic, critically important to managing blood sugar in homeostasis. So delta cells produce a hormone called somatostatin, and then F cells produce a hormone called pancreatic polypeptide. I'm going to wait a little bit because I've got a table that I put together in the next lecture to come back and talk about those and what they do. So hopefully it'll begin to make sense to you that if the pancreas's role is to add stuff to the duodenum, then the pancreas needs to know when the duodenum's got stuff in it. And so the duodenum itself then has to send a signal to the pancreas that it actually has a material in it. So remember in the crypts of Lieberkühn, the downward folds in the small intestine we looked at yesterday, at the bottom we have endocrine cells. And the two we talked about were S cells that secrete secretin, and then CCK cells that produce cholecystokinin. All right. And then we had GIP, which is gastric inhibitory peptide. Okay. So all three of those hormones are going to be secreted by the enteroendocrine cells at the bottoms of the crypts of Lieberkühn. They're going to enter the blood, and then they're going to be circulated to the pancreas and the stomach, where they're going to be active at controlling activity. So if we're just looking at the relationship between the pancreas and the small intestine, then what secretin does is increase the production of sodium bicarbonate. So it causes you to increase more buffer. So as chyme enters your stomach, enters your small intestine from your stomach, and a pH in the small intestine drops, then that triggers the release of secretin, which causes the bicarbonate to produce more, which causes the pancreas, to release more bicarbonate to create the buffer system. Right? And then CCK is going to be released when the chyme exiting the stomach is high in fats and proteins. So you get this chyme exiting the stomach, it's got a high percentage of fats and proteins in it. And that causes CCK to be released. And CCK is the center cells and makes them make the digestive enzymes that are required for you to digest the fats and digest the proteins. So if you think about it, you wouldn't want to be producing digestive enzymes all the time, because if there's nothing in your small intestine, the digestive enzymes are going to want to work on the wall of the small intestine. And so you want to limit the production of these enzymes to periods of time where there are appropriate substrates for them to work on. And then GIP is going to actually, and it's not on this picture, but it would just be another arrow going there. It's going to respond to the presence of partially deconstructed lipids. So remember, we have lingual lipase produced by our tongue. We have gastric lipase produced by our stomach. So we've actually been doing a little lipid digestion. And one of the end products of lipid digestion are fatty acids. So if we have free fatty acids or a high amount of sugar in the chyme exiting the small intestine, then that causes an increased release of GIP. And then GIP stimulates the release of insulin, which is going to be on board then when you begin to absorb the sugars, so that you can manage the sugars within your bloodstream. So the other thing with diabetes, even with people with reasonably good control control of blood sugar is it causes a more rapid aging of your cardiovasculars, particularly the walls of blood vessels. So it's not uncommon for people with diabetes to have increased occurrences of glaucoma, increased pressure in the eye, and also to have more problems with extremity circulation, which leads to ulcers and stuff in the feet in particular. And so it's not uncommon to see people who have been long-term diabetics to have amputations as a so my point was you don't want that free sugar in your blood. Yeah.
So the sphincter only controls the release of these enzymes, but in the other duct that has no sphincter.
Oh, it does.
It does. Oh, okay.
It's my abridged version.
Okay.
Yeah. So, if you look at your picture, the name is in it for that sphincter as well. I always try to balance how you guys know too much and not enough, and try to come somewhere in the middle. Hopefully I manage that. Because otherwise we can spend the whole quarter just on the digestive system before we get into it. We got a lot of stuff to cover. So then our other organ is the liver. And the liver is actually your second heaviest organ besides your skin. Your skin is your heaviest. Your liver's next. Your brain is not very heavy because it's made of lipids. So it's real soft and pliable. Yeah. So what we're going to do is we're going to look at the anatomy of the liver, and we're going to look at the fact that the liver is divided into lobes, and we're going to look at some lobes of the liver. And then the liver itself has this storage vessel associated with it called the gallbladder. And then the gallbladder is there because the liver is making bile 24/7. But you only need bile when you have contents in the small intestines. So during the period of time where there's nothing in your small intestines, you actually need a way to store the bile so that when you have material in your small intestines, you can release a greater amount of bile. Because bile production is a reasonably constant rate over a 24-hour period of time. So when you look at a liver, the liver sits in you like this. So it's in your upper right quadrant. And then the two things you see anterior that is easy to see on the liver are the two largest lobes of the liver. So the largest lobe of the liver is this right lobe, which is this really big lobe over here. And then the lobe over here is the left lobe of the liver. So anteriorly, that's all you can see. So if you turn the liver around so you can see it from the posterior side, then we have two small lobes of the liver. So one is caudate and one is quadrate. So quad is a reference to something with four. So there's actually a ligament on the backside of the liver here, this white ligament. It's called the round ligament. And the cool thing about the round ligament is that it was the blood vessel that came back from your placenta through your umbilical cord and brought the nutrients from mom's blood into your body. And the first place all those nutrients go is your liver. So inside your belly button, what was the umbilical vein in the umbilical cord, inside your belly button runs directly to your liver. So when you were born, they cut your umbilical cord and severed it from your placenta and you. But this part, which is inside your belly button, is still there. So it's a blood vessel that just collapses on itself. And so then you retain it the rest of your life as a little cord of connective tissue-like material that we probably incorrectly call a ligament, because ligaments attach bone to bone. So it's called a ligamentum teres. And then on the back of the liver, it forms this round ligament. So, and it's unfortunate because we'll look at it tomorrow, but when I first dissected the female cadaver in there, where all organs were intact, I carefully cut around her belly button so that I could leave the belly button in place while I removed the rest of her abdominal muscles. And when I did that, this was still intact. You can see it running from the belly button all the way to the liver. But then we flipped her a couple times so we could look at different parts, and it got tore. So I can show you the string piece of it, but it's not attached anymore where it was. So it's really kind of cool. So the round ligament. So then our leg mark for the quadrat, 4 sides, 1, 2, 3, 4, looks square, is the gallbladder on one side and the round ligament on the other side. And then that's our quadrate lobe of the liver. Okay? So then the way the liver sits is it sits against the posterior wall of your abdomen. It's really big because it gets the anterior wall, it gets the lateral wall. The liver is a big organ. And so it surrounds the largest vein that brings blood back up from your lower body, which is called the inferior vena cava. So this big blue vein right here is the inferior vena cava. And this little lobe of the liver that is just left in anatomical position. So on this side of the inferior vena cava is a caudate lobe. Cod is a reference to tail, so it's like the tail of the liver. So it's caudate lobe. So I always try to get people to think about what we know today, what we may know in the future, and how you as professionals in a healthcare environment are going to constantly have to upgrade your knowledge to stay viable in your professions. Right? So you have to be a lifelong learner. So when I went to college, when I took comparative anatomy, I was told the liver does not regenerate itself. So that if the liver becomes damaged, you're doomed because the liver won't regenerate itself. But in today's world, we can remove most of the lobe of someone's liver, transplant it into someone else. Their liver will replace the lobe that was missing, and the part you stick in the other person will grow into a normal sized liver. A little different than what I learned in college. So that's the cool thing about science. We learn more stuff. The reason why is nobody had ever tried to remove the liver at that point in time to see what happens. So, anyway, kind of cool. And then the gallbladder is this green thing. So kind of the cool thing on all the models in here is if it's green, it contains bile. All right? And so and also lymph on some is green as well. But this is our gallbladder right here.
So then what happens if someone has a storage area for bile and someone has their gallbladder removed?
Then you can't store large amounts of it, so you're probably releasing more at a constant rate in your small intestine. And I know both my mother, my mother-in-law, my grandmother have all had their gallbladders removed, and they had to change their diet. There were certain foods that really bothered them. They had really bad diarrhea. So you just can't have that low digest fats. All right. So what's going to happen, and we're going to see this. We're going to see this in several organs as we go forward. And so just so I can kind of tie it together for you. So the liver, we divide the parts of the liver into lobes. In the next unit, we can divide the kidney into lobes, and we can divide the lung into lobes. So the liver, the kidney, and the lungs, we can divide into smaller units called lobes. So if we divide the organ into a lobe, then the smaller part of a lobe, which is actually the functional part of an organ, becomes a lobule. Okay? So the way to think about it is that a lobe is made up of many lobules. The organ itself is made up of several lobes. Okay? So this is a model of the liver, and these hexagonal things here are lobules. So the liver is actually made up of repeated hexagonal-like structures that we call lobules. So if you took a fresh liver and you sliced it kind of thin and you put it under a dissection scope, you could actually see a pattern, a repeating pattern to the tissue. And that would be the lobules that you're actually seeing. Okay? So then the lobules themselves are going to be comprised of what, under the microscope, is classic cuboid epithelium. And these cuboid cells. And so these cuboid cells are called hepatocytes. And it's actually the hepatocytes that are critically important to the function of the liver itself. Okay? And then what happens is there's some specialized capillary beds in the liver. That's what the purple things represent. And the specialized capillary beds in the liver are called sinusoids. So the name sinusoid is what these purple things are. And then we got these mobile cells that appear to be related to white blood cells and may in fact arise from white blood cells. So when you look at the model, they look like little starfish in the sinusoids. And those are Kupffer cells, or if you like the high-tech name, reticuloendothelial the one that looks like a little starfish. So I'll pass this around, and so right in this area, look for a little starfish in the purple area, and that's one of those cells. Those are critical cells because they're the ones that help us destroy aging red blood cells, the Kupffer cells. So what happens is the liver is designed to process all the stuff coming from your large intestine, small intestine, stomach. The first place it goes is the liver. Just like the first place it went from mom's blood was your liver. Then your liver has a big role in processing stuff before it goes to the rest of the body. And then the other thing the liver does is destroy aging red blood cells. So what the liver does is it does its job at destroying red blood cells, does its job at taking material that's coming through the gut lining through the process of absorption and modifying it. And what you can't use out of that process, it creates bile. So in essence, bile is an excretory product created by the liver trying to process the blood. Right? Now the beauty of bile is that we dump it into our small intestine and it helps us digest fats. So the liver actually produces an excretory product that becomes beneficial to digestion. And that's the way the liver gets rid of it, is through the digestive system. So what we have is we have this network of bile ducts that occurs. So when the model's going around, and what you'll see is that we have those columnar cells. And associated with the columnar cells was a very thin, little green, little tiny duct that the cells are lining on the edge. So this is our smallest duct where the bile is collected, is being produced. So that's called a canalicula. So this is a bile canalicula. Okay. And then a number of these little tiny ones coming out of the liver all come together and they're going to form a bigger duct. And so what they do is they're going to form a duct we call a hepatic duct. So the duct coming out of this is going to be a hepatic duct. Well, actually, let's do it first. That's going to become a bile duct. And then a hepatic duct. This bile ducts come together. So now I need my model. Do you guys see this? All right. So you can see the little green thing running through the model right here. That's a canalicula. And it goes to this duct right here, which is a bile duct. And what we're going to have is we're going to have 6 bile ducts associated with each lobule, and they're organized at the bends of the lobule. So we're going to have 6 bile ducts on every one of these. And then they're going to come together to form hepatic ducts. Okay. So what's going to happen then is a bunch of bile ducts come together. from different areas of the liver. And then they're going to form the hepatic ducts. And then eventually what we're going to do is have one hepatic duct from each lobe of the liver. So we have 4 lobes, so we'll have 4 major hepatic ducts. So on most of the models in here, the ducts that you're seeing on the inferior side of the liver are the 2 major hepatic ducts. So the ones you can actually see really well in the model is going to be the left or right hepatic ducts. So if you look right here, there's a little green Y being created by 2 ducts. All right. So the one coming from this side would be the right hepatic duct. The one coming from this side is going to be the left hepatic duct. And what they're going to do is come together to form a duct. So if we kind of draw that so that now we have these 2 big hepatic ducts coming together. And so we'll make this one anatomically to the left and make this one anatomically to the right. Then when they come together, we're going to form a common hepatic duct. So where you see the Y on the bottom of the liver, you see the 2 smaller ones coming together, creating the tail of the Y. The tail of the Y is the common hepatic duct. So now what happens is we've been producing all this bile that's moving through the system. So what's connected to the common hepatic duct is your gallbladder. This is a giant storage organ that's off to the side. So what actually happens is when the sphincter of Oddi is closed and no bile can flow, it builds up so that the bile now gets shunned into the gallbladder. And then the gallbladder stores it. So the duct that goes to the gallbladder is the cystic duct. And to make sense out of that, the hormone we just talked about, cholecystokinin. So cholecystal is a reference to the gallbladder. So if you actually have your gallbladder removed, it's a cholecystectomy. So cholecyst is a reference to the gallbladder, hence cystic duct. Connecting to the gallbladder. Okay? So what happens is the common hepatic duct and the cystic duct come together to form the last duct called the common bile duct. And then the common bile duct joins the duct of Weyerson and forms the hepato-pancreatic and food. That's the entire duct system that you can see. Okay, so I've got a picture that kind of demonstrates that for you, and a little flow chart for you. So what I was trying to point out for you guys at the back of the room, who can't see it very well, is that we have 4 lobes of our liver, so we're going to have 4 hepatic ducts. But usually the ones that are the most common on most pictures is the one here from the left lobe. So this is going to be my left hepatic duct. And this one from the right lobe, which is my right hepatic duct. So they come together to form this duct, which is my common hepatic duct. So here's my gallbladder. And so this duct here going to my gallbladder is my cystic duct. So when the common hepatic duct and cystic duct come together, forms this duct that goes down to this bend in the duodenum. And so this is my common bile duct. There you go. And then the common bile duct joins the duct of Weyerson and forms the hepato-pancreatic food, which is where it drains out. Okay. So that's just kind of the pathway of the duct system that we've been talking about. Right? So this picture is supposed to represent this model. And so if you actually held it like this, then this detail is what we're seeing here. This isn't quite as detailed. So this is a lobule. So this is the functional unit of the liver. And all of the lobules in the liver collectively actually are responsible for producing the bile. And so we produce about 1 liter of bile per day. The bile, depending upon the pigment and the alteration of pigments. So we have a pigment that we can alter its shape. And when we alter its shape, it alters the way it interacts with light, and therefore reflects light differently. So the most common pigment is a pigment called bilirubin, and bilirubin is yellow. So in Romance languages, Latin, Spanish, the word for green is verde. So when it's altered its shape and it reflects green light, then we call it biliverdin, from verde, which means green. Right? And eventually, the bacteria in your gut are going to convert it to something that looks brown, which is why your feces looks brown. And so it's going to be the liver is determining this color. And so if you have somebody who's really starving to death, they can't eat. They actually have bile that's never been involved in the process of digestion. Feces will be green. Right. So what we're going to end up with is water and cholesterol. So one of the things we're going to talk about is your liver plays a critical role in managing fats in your body. The fats we ingest, triglycerides, are not real soluble. So what the liver does is modify them into a cyclic compound, which is cholesterol, and then add proteins to the cholesterol to make it more soluble. And we're going to go through that process. So we ingest cholesterol from plant animal material, and our liver makes cholesterol. When we're young, usually we do pretty good with that. But usually as you age, your cholesterol blood levels go up because your liver is just not managing cholesterol. Okay. So it's kind of, and then there's a gene mutation where really young people have real high cholesterol levels as well. And then it's going to contain what we call bile salts, which sodium and potassium are going to be one of the most common. And it's going to contain some bile acids because there are going to be a couple of acid-like molecules that can attach to them. We'll cover this a little bit. And then the bile pigments, which is the bilirubin, which gives it its color. The bilirubin comes from the fact that we break down red blood cells. And within a red blood cell, we have a heme unit, which is an iron molecule, and it's surrounded by cyclic hydrocarbon compounds. And then this is attached to a long protein molecule. So we can digest the protein and recycle it. We can take the iron off and recycle it, but we can't manage the hydrocarbon compounds. And so that's where the bilirubin comes from. And when we break down the heme unit, we can't recycle those hydrocarbons, and so we end up with bile. So we get rid of it, and we reprocess everything else. We're going to do that in more detail when we get to blood, how that process works. Because then we'll talk about the formation of hemoglobin in more detail. So if we have an overview, hepatocytes produce bile that's transported through that system for temporary storage. And then bile is, as I said, partially an excretory product, but then it becomes very important to digestion because bile emulsifies fats. So what is an emulsifier? Yeah, not molecules, but large aggregates of fat in small aggregates of fat. So the way you can see it is if you went to the grocery store and you go to the peanut butter shelf, then there are peanut butters where they don't separate and then the oil doesn't come to the surface of the peanut butter. And then there are the peanut butters where the oil separates out. The ones that don't separate have an emulsifying agent. The ones that separate out lack an emulsifying. And what the emulsifying agent is doing is as Laura said, it's actually making the fat droplets little tiny droplets, so they stay suspended in the matrix of the peanut butter batter. But if the fat droplets aggregate into larger and larger big droplets of fat, they float to the surface. So the way in which most dishwashing solutions work to actually help you clean your dishes, particularly with fats, is they have an emulsifying agent that makes the fats into little tiny droplets. So what you can do is you can get a jar, you put water in it, put oil in it, and then you get another jar, put water in it, oil in it, and dishwashing soap in it. Then shake them both up really hard, and then go to bed tonight. Then in the morning, all of the fat that was in the jar without the emulsifying agent will be on top of the water. And you'll have two separate entities in your jar. The one with the detergent will all be in little tiny droplets, still suspended in the water. And that's what bile does for us. So the problem is, if we have this giant glob of fat, and we have the enzyme lipase that's going to digest it, then look at the volume to surface ratio there. And so it's going to be really hard for this enzyme to digest this giant thing. So what if I convert this giant thing into millions of these little things that lipase can interact with? Now we've got an amazing surface area to volume ratio. And that's what emulsification does for us. There's actually a compound that you can use to lose weight, and it changes the way fat behaves in your digestive system. And it decreases your capacity to emulsify it and get it in the swell droplets, so you don't absorb as much fat. And that's how you can lose weight. But the problem is all the fat then gets in your rectum, sits up on the top of your anus. The fat is like a lubricant and it oozes through the anus all the time. So if you read the labels closely for that compound, it says may result in anal leakage. There was one brand of potato chips or something. Yeah, Wild Chips has it in it. And so if you eat a bunch of them, yeah, I guess it's too much. Okay, so what we're going to do is we're going to emulsify fats. And so we do it because cholesterol is a type of fat, and so that helps with interacting with the other fats to emulsify. Well, what actually happens is if you store this bile in your gallbladder, and as you age, you have problems controlling. You actually begin to have problems controlling blood cholesterol levels because your blood cholesterol is going up. The amount of cholesterol in your bile is going up because you're not managing it as well. So then what actually happens is as the cholesterol content in the bile increases, it precipitates out a solution and it forms crystals. So you end up with these cholesterol crystals, and they form the beginning of these bile stones that then form because you're concentrating your bile too much. So that's why we typically see gallbladder problems with elderly folks and not younger folks because of that process. So I actually, former students always like to share things. So these are the gallstones from one of my former students, and they had to completely remove their gallbladder because it was totally filled with this stuff. So you can actually see the shape of the gallbladder with the stone, and you can pass it around. And then here's just a bunch of small ones they removed from a gallbladder. So those are gallstones. And so what we normally do is we have some drugs that will help dissolve it. If the drugs don't work very well, then we use sound waves. And we try to take those big stones and break them into little tiny stones it can pass down through the common bile duct. And then if this lithotripsy, which is the sound waves, doesn't work, then it's surgery. So it's a 3-step process. Some people just go from, oh, you have gallbladder stones to surgery because they're so advanced when they finally show up in the clinic that they just have to do the surgery and don't have time to do the... That was the way my mother was. She'd been feeling bad for a while, but she's a nurse. Nurses make bad patients. And so she just didn't do anything. Went to the doctor finally, went to the emergency room because she got so bad. And she was somewhere else. She wasn't at home. And so the guy says, well, you need to have your gallbladder removed. She says, well, then I'll just drive back to my place. And I'm going there in a month, so I'll do it in a month. And he says, no, you won't. You'll be dead in a month, so you're not leaving the hospital.
Does surgery always mean removing the gallbladder, or can
No, sometimes they can go in and try to remove the stomach. All right. So the other thing that the liver does is it processes all of the blood coming back from your digestive system. So there's a cool pattern to this, and then we can talk about it. All right. So where we're doing all of our absorptions in our small intestine all coiled up in the center. And then we have our large intestine going around it. And so what we end up with then is arteries carrying blood to capillary beds to this whole system. Okay? So what we have is an artery leading to a capillary bed. And so tying this together with what we talked about yesterday, then the capillary beds in the small intestine would be in the lamina propria, and these capillary beds would extend up into the villi. And so that's how we absorb things. Okay. Now the problem is we've got a bunch of stuff we're absorbing that doesn't carry well in blood. So we don't just want to send it back to our heart where it's going to be pumped all over our body. So what we want to do is we want to send it through the liver first. Okay. So what actually happens then is that we go from this artery feeding the capillary bed, and the capillary bed is going to be associated with the intestines. And then what happens is all of these little veins come together and they form another vein. And in normal circulation, arteries carry blood away from the heart and veins carry blood to the heart. But in this instance, our liver is in the way. So we have our liver here. And within our liver, we're going to have a second capillary. And then what we're going to do is drain the liver back to the heart via a vein. Okay? So what we end up with is a joint capillary system, where we have artery, capillary, vein, capillary, vein. The normal pattern is artery, capillary, vein. Okay? So anytime we connect two capillaries in a sequence, we have a portal system. So a portal system is where we've connected two capillaries in a flow sequence, all right? So then what we're going to do then is we can use that as a descriptant to identify things. So since this portal system involves a second capillary system in the liver, and it's a hepatic portal system, because hepatic is a reference to the liver. Okay? So then what we can do is then we can identify this vein as the hepatic portal. And what it does is collect all of the blood that's gone through the capillary beds in the intestine and sends it to the liver. That's how we process everything that comes out of comes through the gut lining with our liver before it goes anywhere else in our body. So when you look at any of these models of the liver, then I chose this one just because they color coded it for you. A lot of them are color coded, but notice that we have this nice blue vein. And that indicates a vein that would be a normal vein carrying blood back to the heart. We have this red thing, which is the artery carrying blood from the heart to the liver. Now we got this funny purple vein in the inferior aspect of the liver. The purple was to denote a portal vein. So on some of them it's just blue. But the big vein you're going to see on the inferior aspect of the liver is the hepatic portal vein. Okay. And that's where all the blood coming back from our small intestines goes to the liver first, where we can process it. Okay. It's kind of a cool system. And so that allows us to modify carbohydrates, lipids, proteins. We can remove drugs. So one of the things that the liver does a great job of removing out of your blood is alcohol. So if you consume way too much alcohol, it damages the liver, because the liver is the first organ trying to detoxify. So the other tissue in the body that can detoxify alcohol is skeletal muscle, which is why men typically can drink more alcohol than women, because they have a greater muscle mass. But the fascinating thing about alcohol is the enzyme that we use to detoxify it is an enzyme that doesn't exist if you don't drink alcohol. You don't need to make it. So if you haven't ever drank alcohol, the first time you drink alcohol, the enzyme's not there. One drink. And then there's cultures like Native Americans who don't make alcohol dehydrogenase. So that's why they have trouble with alcohol. They don't. Well, traditionally no, but the more new genes have been added through interaction with other groups of folks than this. But we used that, and we sold alcohol to Indians and paid people good during the Indian-American wars, which is why this whole campus is here. This was a front during that time. We sold alcohol to them because they would get drunk really easy. It's really hard to fight well when you're drunk. Because they don't actually produce that. And there's a couple other cultures that don't. So Europeans have been playing with fermentation for centuries. So Europeans have electric production of alcohol.